Alright guys, go ahead and open up your notes. We can start out with a little check on learning, because again, reminder, we have a test on Friday. So just to see how are we doing with what we just went over yesterday. Alright, so the first question up is, what is the name of the layer of sediment or rock that does not allow water to pass through it? Right, so when I'm thinking water can't pass through, the first word that comes to mind would be impermeable. Second word that comes to mind to me would be clay. So with that, I'm going to cross out permeable layer. Then I'm going to cross out aquifer. And then I don't think I've heard of non-aqueous. I mean, I have, but you haven't. I'm trying to think about it from your perspective. That only leaves us then with B, and aquiclude. So again, remember, we're talking clay, we're talking impermeable. All right, good stuff. Check the next one. Okay, here. Which sequence of terms correctly labels the features shown in the diagram? So over there we're seeing that we have the land surface, the grass, then we have an area where it doesn't look like there's much water, the top, or a boundary between the two. All right, so when we look over here, we're looking at 1 as the zone of aeration, and 3 as being the zone of saturation. And remember, 2 right in the middle is going to be the water table. Down at the bottom for 4, if you're wondering what that is, it is an impermeable layer. That might either be an aquiclude, that could also just be some bedrock. All right, let's look at the next one. All right, here, which layer do the pores contain mostly air, although the materials are moist? And that's a perfect description of layer 1. Again, that's the zone of aeration or the unsaturated zone. So it doesn't mean that it's dry. It just simply means that you haven't filled all of the pore space with water. All right, go ahead and take a look at this one. Hit pause, try to answer it. All right, so what conditions are required for the formation of a spring? Remember, the water table, whether it's elevated or not, needs to come in contact with the surface. All right, so we need, in this case, we have an impermeable layer. We have an aquiclude that is preventing the water from seeping all the way down, and therefore you're getting that spring to pop out, elevated above, and then flow down. So then what choices do we have? So let's cross off the things again that are not going to make sense. So I'm going to work it in reverse here. An aquiclude defines the main water table and recharge from above. It's not defining the main water table. An aquiclude holding water above the main water table and recharged from above. Maybe. An aquiclude holding water above defined areas of aeration and saturation. Ooh, that one sounds better than the last one. And then defined area of aeration, saturation, and impermeable layer. That's not really helping me to understand the formation there of the spring. So overall, I'm going to go with B. All right, again, take a look at this question, hit pause, try to answer it. And this one we've talked about a couple times, the fact that porosity doesn't necessarily mean permeable, right? The pore spaces must have an interconnected ability to transmit water. All right, so the focus question here, how does groundwater interact with the land? We've talked about this in a couple different aspects, right? So we have springs, we have streams and rivers where the groundwater now seeps out. We've also talked about the wetlands, and the fact that if the water table sits really high, right, we can have a moist area. If we have an area where water settles in, like the swamp, where the soil remains saturated year round, all of these different ways, we're seeing that integration. And then we talked yesterday about wells, right, and the fact that that's our water source. Again, we're able to pull that up, put it out onto the land, and then that seeps back down, creating this cycling. Now we're going to take a quick second and look at some chemical weathering. You guys did this last night in your homework when you read. I'm saying that with the assumption that, of course, you did the reading and answered the questions and not just answering the questions. All right, so if you're a little lost right now, you know where you need to go back and fill yourself in. Okay, so hydrolysis, remember that that's chemical reaction of water with other substances. And today we're going to look at carbonic acid, so water plus carbon dioxide, and how it's going to react with limestone and really with calcite. So you may recall that most groundwater is going to be slightly acidic due to carbonic acid. We get carbon dioxide in the atmosphere that then dissolves into rainwater. And we also actually pick up a little bit of carbon dioxide in the soil. We can pick up some other elements, make some other acids, but that's beyond the scope of what we're doing. All right, so let's see how this happens. And this is going to be broken down into 3 steps. So first, carbon dioxide, CO2, plus H2O combine to form carbonic acid. And you see right there, CO2 plus H2O yields H2CO3. And that should be a review because we talked about carbonic acid back when we did chemical weathering in the first trimester. Now this is where it gets fun. In the second reaction, carbonic acid splits into hydrogen ions. Remember, that's the power of an acid, right? The availability of hydrogen, right? It splits into a hydrogen ion and bicarbonate ion. So that's where you have the HCO3. Then the next step is that now free ion of hydrogen goes and attacks the calcite. So the CaCO3 reacts with the H. That's where we saw the effervescing, the bubbling. You guys remember when we dropped acid on the calcite and you all saw the little bubbles grow on top and you kind of like gassed off? Well, that reaction is the hydrogen breaking in and basically freeing up a calcium ion or calcium ions, and then you have additional bicarbonate left over. So that's what you're seeing in these different reactions right here. I'll just pause for a second and remind you guys this is not a chemistry class. Simply want you to understand where carbon dioxide and water make carbonic acid, and then the fact that that carbonic acid splits apart and will be dissolving the calcites, and those calcites in a minute we're going to see are in the limestone that make up karst topography. All right, so this set of notes right here reminds us that dissolving or dissolution and precipitation of calcites play a role in the formation of limestone caves. So a cave or cavern, if you've been to like Howe Caverns, you know that it's a big underground limestone cave. The groundwater was able to seep in, was able to infiltrate into the cracks, and then started moving or collecting in a horizontal pattern and dissolved the limestone in an initial crack that gradually grew larger and larger and larger. If you think about it, you keep splashing acid in this small crack, that small crack's going to keep dissolving upward, downward, side to side, and it's just going to keep growing and growing and growing. There's still plenty of support around. So if it helps you to piece it together, think about the acidic groundwater being like chemical miners, right? When a miner goes down, they're going to mine for some coal. They go down and they hammer and they chip away at the rock. Now they take big sections of rock out, but here it's a slow process where the water and the acid's able to just keep chipping away, chipping away, chipping away, and slowly it makes a larger and larger and larger opening. Now, when the water table drops, then we can actually go and access that area. And that's what you see in this diagram, right? So you see the infiltration in the top diagram, the water table's riding high, and that groundwater has the acidic carbonic acid in there. So because it's limestone, and limestone has calcite, it can dissolve and open. And as you see, these little cracks up in here, right, these little cracks that are up in this area, now become big, large openings. Now I'm going to pause on that bottom diagram because you're pointing out stalactites and stalagmites. Stalactites, we're going to see in a second, are called dripstones. So as you form that cave, you might actually have more infiltration happening. But that infiltration and that dissolving, again, we said before, frees up calcium. Not calcite, but calcium. So when the water comes down and it goes to drip from the ceiling, the water's going to leave, the H2O is going to leave, and it leaves a little bit of the calcium behind. So that calcium then makes this dripstone. If the calcium comes down, stays in the water, and then it drips and splashes, when the water splashes, it may leave the calcium on the floor. And that's where the stalagmites are going to form. Definitely need to know stalagmites and stalactites for your test. All right, now, sinkholes. Sinkholes happen when a cavern, which you just saw in the last picture, right, when the top of a cavern collapses. So think about this scenario, right? I'm going to scroll back. You have this whole underground feature, and in that feature, right, I'm going to try and get a better pencil here. See if this works. Right? You keep having water coming down, coming down, coming down, coming down. If we weaken along the edges, along here, and this part keeps thinning out at the top, what can eventually happen is this whole section that I've now covered blue can all fall into the hole. And if there's anything above, well, now that falls in the hole as well. And that's what we refer to as a sinkhole. Sinkholes are very, very common in Florida, right? Every year you hear of a sinkhole collapse, and it's just one of the risks you take by living down there. Puerto Rico has other sinkholes, right? All because they're in a limestone-rich topography. And rather than going limestone-rich topography, they use a really cool word called karst topography. So karst topography means that you're in a limestone-rich region that is susceptible to sinkhole collapse. So it's just one of those risks you're going to take by moving down there. Okay, other than the collapse, what we just talked about with dripstones, right? Dripstones are rock formations that are built over time as water drips through caves, right? So if it drips from the ceiling, or it or collects down on the bottom, we're going to get those dripstones. And those dripstones then are going to make our stalactites. And I'm just going to highlight here the C in stalactites because they're going to form on the ceiling. So stalactite, ceiling. And then on the ground, right, we're on the ground, we're going to have stalagmites. So it says on the floor. I just think ground, stalagmites, and then stalactites. But you get this, and you get that, and it's all because of the dripping of that water that has dissolved calcium, right? And you should have written in your homework calcium for the mineral in dripstones. It's probably a good time to remind you that your homework was due. Thank you. All right, so let's follow up on this. What forms when carbon dioxide dissolves in water? All right, hopefully you all just said carbonic acid. Which is a natural underground opening with a connection to Earth's surface? Okay, well, I know it's not stalactite and stalagmites because those are both dripstones. Oh wait, that says dripstone. Process of elimination. Folks, I'll keep modeling that test-taking strategy all year long. As soon as you start using it, your test scores will improve. All right, next one. Which is not associated with the dissolution of limestone bedrock. Which is not. And with that, we got deltas, right? Because sinkholes are the collapse, karst topography is limestone, and disappearing streams. Ooh, we didn't talk about those. So disappearing streams can happen when a stream is flowing along, and then it hits one of those cracks or small sinkholes in limestone rock, and the water literally just gone, just seeps right into the ground. So disappearing streams, really, really cool. Just another feature that you can find in a karst topography. Which characteristics do most areas with karst topography share? So, the first thing I know is I need to have limestone. So anything that doesn't say limestone, I'm crossing out. Then I said Florida, Puerto Rico. If you think about Florida and Puerto Rico, they're definitely not dry. They are humid. And think about it, humid chemical weathering. We said warm, wet are the best scenarios for chemical weathering. We said that in the first trimester. Now we're seeing how we actually apply it. So again, humid areas, limestone beds. And now, hopefully, you feel comfortable answering that question that we started the chapter with, which, how does rainwater get into this underground cave or cavern? All right, so guys, that wraps up for today. Go ahead, if you need to go back and fill in any of your notes, do that, and then go ahead and start your homework. Thanks, guys.